So, our topic for today is section 10.3, which is parametric equations and calculus. It's a natural continuation of section 10.2. And basically, well, last time we mostly analyzed the pre-calculus questions. So how does it look, how do we graph it, and so on. Here we want to ask a couple of calculus questions. And basically, I would say that the whole section boils down to two formulas. So what are they? So formula 1. For this section, and formula 2. And then we'll just do problems to practice how it all works. What is formula 1? We have the following. So here is the function, here is x, here is y, but generally we are here at point A, and function is given parametrically. So x equals f of t, y equals g of t, and then at certain point, moment t0, f of t0, g of t0 is basically point A. So we are at A at time t equals t0. Okay? And then what do we want? We want to find slope of a tangent line, which is obviously one of the most important questions in calculus. So we want this tangent line, and we want slope of the tangent line. So here is the formula. So dy over dx is equal. So we actually do the following. So you can write this in a few different ways, and that would be dy over dx is f prime t g prime of t is y. G prime of t plus y is g over f prime of t, which is what? Which is basically dg over dt over df over dt, if you write like this notation. And generally, formally, it looks like we got y over x, and then we just divide it because dg is actually dy. So we get, and we can write it like that. So it's dy over dt over dx over dt. So here it is. So it looks formally like we divided by dt. It's not really division, although if one involves differentials, one can actually argue that really what we did is not division. But a little more details, of course, what? We are calculating this at x equals, so if f of t0 we call x0, and this we call y0. So this is dy over dx at x equals x0, so at that point is actually quotient of those derivatives. But now we plug in time, t equals t0, the same thing here, t equals t0. So this is mathematics. When you plug in something, you just put a vertical line and specify what is it that you are plugging in. So just calculate, of course, there are some conditions needed. What are the conditions? If f and g are differentiable, t0, that means if those two derivatives exist, and what else? And of course f prime of t0 is different from 0, because otherwise you cannot divide. What happens if that's equal to 0? Then we just cannot call formula. We have to do special analysis and see what happens, and we will see some problems. By the way, how do you derive this formula? It's absolutely trivial. So what would that be? So it's not proof, but just argument. Why would that be? So dy over dx is actually what? Limit when h goes to 0. What would that be? I need language here, so it's y of x plus h minus y of x over h. This is the definition from calculus 1. But then what is h? H is actually, it's better probably to do the definition of x 1 y1 minus y0 or y minus y0 or x minus x0 when x approaches x0, because that's what it is. You do rights overrun, and then when x goes toward x0. And then what do we do? In the case of differentiability, we'll say we'll divide both of them with t minus t0. And then what? If t is, since function g of t is differential, f of t is differential, then what happens? When t goes to t0, then also x goes to x0, because f of t is differentiable, so it must be continuous. So generally it will be a limit when t goes to t0, and then on this quotient. And what would that be? Then if both limits are non-zero, or if the bottom limit is non-zero, then we can separate. We get limit when t goes to t0. Y minus y0 is basically g of t minus g of t0 over t minus t0. The same thing for x here. Limit when t goes to t0, and this is g prime of t0 over x prime of t0. I rushed this a little bit and squeezed it here in the corner. I wanted you just to have a feeling of how is this being, why is this formula true? All right, what is formula 2? Formula 2 addresses different question with the same curve, and that is, we have a point A on the curve, and we have point B on the curve, and we want to calculate the arc length, so arc length. So that will be a length of the curve, length of the segment AB. And here's the formula, and we'll explain it in a minute. So let's say that A, we arrive at A at the moment t equals A, and we arrive at B at the moment t equals B. So that means what? That those coordinates here are f of A, g of A, and here is f g of B. So length of this interval equals, again, if both functions are differentiable, where? Everywhere between A and B, then it will be integral from A to B, square root of f prime of t squared plus g prime of t squared dt. So that's the second formula. So generally, there are two formulas to remember. This one is a little crowded. Let me erase everything around it. My suggestion is just memorize. Here it is. Erase this derivation. So here is the formula to memorize. So g prime of t over f prime of t, or y prime over x prime. Here's the second formula to memorize. Little comment, why is that? I'm not going to write the formal proof, but generally the main idea for this theorem is basically Pythagorean theorem. So what happens is the following. Let me make this AB a little longer, like this. So here it is. And let's say, so here is the timeline, here is A, here is B. So here we are at point A, and here we are at point B. So what do? We divide this interval into tiny little intervals. We are actually building a Riemann sum. So each of them we'll call delta t. So here is each of them is delta t, delta t, delta t. And then what do? Generally, then they're dividing point. This is t0, t1, this is tn. As I said, we don't have to be too precise for this, just I wanted to get a feeling for it. So generally, when you plug in different times, then we'll have one point here, A1, side A2, and so on, and let's say B is actually AN. So this is A0 of my A, and B is actually AN. So we are dividing time and calculating our position at those times. And here is the crucial idea then. Then our arc length is the sum of those little tiny intervals. So why are we dividing into those tiny intervals? Because on a short interval, I can assume that the arc length is equal to this chord, to this segment. So generally we are approximating, and if these are short segment, our loss is minimal. So let me pull out one of those segments. So it looks like this. So this is, so if my chord goes like this, but we connect it this way, then what would happen? This would be, what? Then this would be change in x. So this would be what? X of Tn, Ti plus 1, let's say, minus x of Ti. This would be y of Ti plus 1 minus y of Ti. So this is between point Ai and point Ai plus 1. And generally what? We generally just get Pythagorean theorem. So we get the following expression: x of Ti plus 1 minus x of Ti squared plus the same thing, y of Ti plus 1 minus y of Ti squared. But how do we get, and the square root? So everything is there, but I have differences, I don't have derivatives. But then what? Using mean value theorem, we can say, all right, this is equal, actually, x prime of some point Ci that's in between times delta t. And this is squared. And this is the same way, y prime Ci delta t squared with the square root. And then, when we take delta t squared out, we get square root of x prime Ci squared plus y prime Ci squared. Here is your delta t. So that's each of those little segments. You take the sum when n goes, I goes from, let's say, 0, from 1 to n, from 0 to n minus 1, precisely, because I know left side. And we take a limit when they are equal, or wherever diameter of partition goes to 0, or roughly when we have infinitely many equal segments, and this is exactly Riemann sum for this integral. So generally, though this is sum of the squares of derivative, is generally coming from Pythagorean theorem. There is, we can make even more common sense here using physics a little bit. Why? Because what? If f of t, g of t is the position vector, I don't know how there are vectors, then when you differentiate, you get velocity. Magnitude of velocity, and that's exactly what this is. This is magnitude of velocity. It's actually speed. So what do you do here? You take speed times times to get distance, and then you add up little distances and you get the sum. So mechanically, it also makes sense. So altogether, there are two formulas, and now we'll just do the problem. Let me actually erase everything and just have my two formulas in the corner to call them when we need them, and that's it. So formulas, and that's what you need in your sum here. So let's say formulas. So formula 1 is what? dy over dx equals dy over dt over dx. Formula 2. length of the interval AB equals integral from A to B square root of x prime t squared plus y prime t squared dt. Where of course A stands for what? X of A, y of A. B stands for x of B, y of B. And there are some conditions, and that is that this is different from 0 and the functions are differential on the interval. So here is the summary of everything we did so far in this lecture, and that's basically the only thing you need. So let's go problem by problem and practice on this. So here it is. Example. Find the tangent line for the curve C defined by x squared over 4 plus y squared over 16 equals to 1 at which point and point M 3 root 2 over 2 and y, where y is greater than 0. What is this? You don't even have to draw it, but generally it's an ellipse, like this. Here is that point M with undisclosed y coordinate, and we want equation of the tangent line. So this is the simplest and kind of most trivial problem of this type. But what we'll do here, of course, we can do implicit differentiation, and that's how we did this in section 10.1. I want to do this time using parametric equations, and that's a very important skill for calculus 3, that you learn how to parameterize ellipse and circle as a special case. So let's pay attention. It looks trivial, but somehow students do not always perform too well on this. So let me just carefully go through this. So the crucial thing is, actually, when you do parametrization, to build that one here, and then it's very easy. Whoever's this guy, that is cosine squared t. Whoever's this guy, that's sine squared t. That's it. That's our parametrization. Sounds reasonable because cosine squared plus sine squared is 1, so there's nothing bad here. So generally what? So now I just square root it and I'll see the following. So here's parametrization. X over 2 is cosine t. I square rooted this, right? X over 2 squared. And then y over 4 is sine t. Here it is. And then you go around however you want. I'll do the standard one. T goes from 0 to 2pi. Here it is. That's my parametrization. Of course, now what? That 2 can go to the other side. That 4 can go to the other side. And here's my ready-made equation. And then what? I have a little problem. What is my problem? My problem is that I don't have y coordinate, and I will need it. So I'll calculate that, plug in x, solve equation easily. And then I also need the value of parameter. A crucial thing here for this formula is not to know position, to know time. But we'll recover time quite easily. So recover y. Recover y, that's first step. So what do I do? Plug in x, I'll get what? 9 times 2 over 4. 9 times 2 over 4 divided by 4. Now why am I doing it this way? No, what's better? Multiply by 16 first, so we get 4x squared plus y squared equals 16. Why would I work with fraction for no good reason? Now I plug in what I said I'll do, so 4 times 9 times 2 over 4 plus y squared is 16. 4 and 4 cancel. Y squared I got something wrong here. Let me see what. So 3 root 2 over 2. When I go here, 9 times 2 is 18 quarters, which is 9/2 foreign. That's too big. Did I copy the problem wrong? Oh, I copied my equation wrong. So it's x squared over 9. That's where I copied it wrong. Sorry. So what would happen then? Okay, not a big deal. So we'll, so generally here we'll get 3 cosine t. That's the only difference. Everything else is the same. And then here's now a little different. When we recover y, what do? Here we multiply by 144, so we get 16x squared plus 9y squared is 144. And then recovery goes the same way. So what would that be? When x is 3 root 2 over 2, so we get 6 times 9 times 2 over 4 plus 9y squared is 144. So this will be 72, I think, because 4 times 2 is 72. Plus 9y squared is 144. 9y squared when I subtract 72. So y squared is 8. Y is plus or minus 2 root 2, which is square root of 8. But then they told us to pick a positive value. So y is plus 2 root 2. All right, let me check my calculation better before we get into bigger trouble. Good. So I have position. So position is what? 3 root 2 over 2 and 2 root 2. So we want the equation of this tangent line. I can start it. I like to start that before I get involved in too much calculation. What is that? Y minus 2 root 2. Slope is missing. X minus 3 root 2. I like those and x plus b. I don't want to waste 2-3 lines on calculation. This is ready-made formula. Y minus y value, x minus x value gets ready for the derivative. But in order to use our formula 1, we need to recover time. So we want to see when are we at this point when we use parametrization. So I want to use parametrization. So x equals what? 3 cosine t. Y equals 4 sine t. And I want x to be whatever it says, 3 root 2 over 2. And I want y to be 2 root 2. When I solve for this, I need that cosine t is root 2 over 2. And sine t is root 2 over 2. And then it's obvious what is the angle that has cosine and sine root 2 over 2. That angle is pi. So now I have time. And then what happens? I've calculated x prime and y prime. So y prime of t is how much is 4 cosine t. X prime of t is a negative 3 sine t. So I'm not going into formula because I just want to prepare the pieces and then say t is pi over 4, we said. So then we'll get that y prime 4 is what? 4 cosine pi over 4, which is 2 root 2. X prime of pi over 4 is negative 3 sine pi over 4, which is negative 3 root 2 over 2. And that's it. Formula says that my slope m equals y prime of t 0 over x prime, which is this formula. So just divide two numbers. I very often mix them up. Who goes first, who goes up, who goes down. It's obvious, but just if you're in a hurry sometimes, because we write numerator first. All right, anyway, y prime is 2 root 2. X prime is a minus 3 root 2 over 2. And it's not 0, so everything is okay. I can cancel root 2 and root 2. The answer is negative 2 times 2/3, which is negative 4/3. This calculation squeezed in here, but that's the one. So I put negative 4/3 here, and we in order. So that's how this problem works. This is probably the most important problem in the whole section. All right, let's see variation of this problem where we sometimes ask some more interesting questions. So here it is. Problem number 24. This will be a busy problem. Less trivial than what happened here because geometry is more complicated. So here it is. Problem number 24. The curve is given parametrically. X equals t cubed minus 6t. Y equals t squared. It says, find the equations of tangent lines at a point where the curve intersects itself. So generally, the trouble here is that we don't see very clearly how this looks like, and I'm not sure how to find that point where it intersects itself. When I find that point, then we'll just call machinery. So this pre-calculus part is a little more complicated than the calculus part. So generally what? Probably here, if I had a calculator here, I would definitely use calculator to see how it all behaves, and I'll show you that in the part when I do the calculator video. So if I'm doing it by hand, then I will just examine a few points. What is the first observation? That y is always non-negative, so this will stay above the x-axis all the time. What else? X is obviously odd function of t because both powers are odd. So, so that means if I use positive time, if you compare positive and negative time, then y is the same because you are squaring positive and negative, and x switches position. So basically, there will be a symmetry with respect to y-axis, but you don't have to analyze it in too many details. So here is t, here is x, here is y. But because I observed that, actually I'll save some time and start with positive with t equals 0. So when t is 0, I get 0 as well. So here is 1 point. And then what? So x is basically equals t times t squared minus 6. So generally x will be 0. X will be 0 when t is root 6. Plus or minus. So when t is plus or minus root 6. So what will happen with x? It will start with 0, and then, so you can analyze this function t times t squared minus 6. Just the positive part. Here is 0, here is root 6. That function in the beginning is what? If your t is small, then this will be negative, and then it will be positive, and then it will stay back. So generally what happens is, so between 0 and root 6, so let me do t equals 1. So I didn't do this analysis, I'm just playing with it. So when t is 1, x will be negative 5, and y will be 1. When x is 2, it will be negative 4, and the y will be 4. And then when x is 3, when t is 3, sorry, then x will be what, 9, and y would also be 9. So generally we cross that square root of 6. So that square root of 6, x reaches 0, and y reaches 6. So generally what happens is that this curve will go sharply left. You see -5 and 1. So it will go sharply left, and then we'll come back, reach 0, and continue. Maybe too little. I just strengthen it too much. So this is what happens, and then it will continue this way. That's a positive part. As I said, if I took negative time, then I will have the same y's, but and I can plug a few. So if it's -1, I'll get 5, 1 at -2, I'll get 4, 4 at -3, I will get -9. So generally what happens, the curve will be coming the same way it's leading here, will be coming from here, across here. So here it is. So this is the whole flow, and that's what calculator will show you. So this is the position at t equals √6 and t equals -√6 also gives 0 and 6. So that's the point of self-intersection. So we just found it by luck. So here is that point A, 0 and 6. And at that point, curve visits that point twice. Once coming in negative time, then circling around. This should be smoother. Right there. See the reason for cusp there. So that's it. What would be the way? So I just by accident ran, or by slight analysis, ran into the point where curve intersects itself. What would be machinery if I were not able to see it from the graph? So what would you like to do is the following. Track it algebraically. Track it algebraically. So I want 2 different times. I'll call them t and z. So different times, I have to call them differently. T and z give the same x and y. That means same position in 2 different times. And then what do I do? First position will give you t cubed minus 6t. And second will do that at z. And then at the bottom, t squared would be z squared. And here's the system, and when you solve this system, hopefully you will get √6 and -6y, because from here I get t equals plus or minus z. It cannot be plus z, because then the times are equal, different times. So t must be -z. So from here, different times. So it says t equals -z, or z is -t, which is the same thing. And then what do? I plug it in the upper one, so I get t cubed minus 6t is -t cubed plus 6t. I place -2 for z, then when I go to the left, I go doubling 2t cubed minus 2t equals to 0. I pull out 2t, t squared minus 6 is 0. So t is not 0, because if t is 0, t and z are equal. We said it's not, so t is not 0. So t squared must be 6. And then I can say the following. Those 2 different times, and let me, let t, if they are not both negative, let t be the positive one, and z negative one. It doesn't matter, because names are arbitrary. So in that case, t, because t is plus or minus √6, so I choose t to be √6, and z to be -√6. And here is, we got those 2 times, and we got the position. So what is the position? X is what? T cubed minus 6t, which is 0, and y is t squared, which is 6. So here is algebraic way. We already have that. And that's it. This is the only demanding part of the problem now. When we know that, then just we call our formula. So now everything is trivial. So what? At t equals -6, -√6, that's the green one. Green part. Then what do we do? Then we get what? X prime is 3t squared minus 6. Y prime is 2t. So at t equals -√6, what are we gonna get? X prime -√6 is 18. y prime of negative root 6 is negative 2 root 6. So slope, green slope, M1 is what? Negative 2 root 6 over 18. I usually don't rationalize denominator, but this is so inviting, so if I multiply by no, it's not inviting, because it's out here, so sorry, minus root 6 over 9. Is this correct? Check. And my x prime is wrong, whatever that happens, whatever happens, 3t squared minus 6. Oh yeah, sorry, this is 12. Why? Because when we plug in root 6 squared, 6 times 3 is 18, minus 6 is 12. So this is minus root 6 over 6. So then equation of that tangent line would be what? Y minus 6. Equals negative root 6 over 6 minus x minus 0. And then it's very easy to see when t is just the root 6, everything will be the same, just x prime would be x prime of root 6 is 12 again, but y prime of root 6 would now be y prime of root 6 would be 2 root 6. So m2 is positive root 6 over 6. So then here's our answer. Those two tangent lines are what? Plus or minus root 6 over 6. So it's fairly flat. So here it is green one with a minus, and then orange one is orange one with a plus, and green one with a minus. And that agrees with our drawing, so this is negative root 6 over 6. This is the slope root 6 over 6. So applying formula was fairly easy. The most creative part was actually to see how it all looks. We are not maybe used too much to see curves that intersect themselves. So this is very nice and kind of a valuable problem where I hope we'll learn a lot. A couple of other problems. Very often we ask you the following question, and the question is, find the points of horizontal and vertical tangency. So these are standard calculus 1 problems, just in this new language and a new technique. So what would that be? So problem number 26, it says here. So find the points. So here is the curve x equals t. Y equals 2 times 1 minus cosine t. And it says negative 1 lesser equal t lesser equal to 2. Oh, that sounds strange, but it seems that that's okay. So what can we say? So we are considering, so we want points where tangent line is either vertical or horizontal. So where will it happen that tangent line is vertical? Oh, horizontal is easier. Those are the ones, if you look at this quotient, where y prime of t0 is 0, but x prime is not. Then we are allowed to use formula, we divide, we get 0, and that's horizontal, slope is 0. Tangent line is vertical, then it goes the other way around. Y prime of t is 0. It's not 0, but x prime t0 is 0. We don't have that formula because we are not allowed to use that formula, but generally what happens if you look at the proof, then if when this number, when you're approaching t0, this number is getting smaller and smaller, this one is around the constant, so whole expression goes to infinity, and that's infinite slope, and that's exactly a vertical tangent line. But what else could happen? there might be a case where both of them are 0. Then we don't know, we have to analyze it individually. We cannot call formula, then just replace a limit and try to play with it. So what happens in this case? Solution, x prime of t is just 2. So that means this is never 0. What about y prime of t? Is 2 sine t. And when is this equal to 0? This is equal to 0 when what? When t is 0 plus k pi. T equals to k pi. So that means sine is 0 when you are here and here on the circle. So which points are in our domain? T equals 0, t equals pi, and t equals 2 pi. One can argue that since 2 pi is not completely in our domain, it just has a half, that would not be a tangent line, but that is basically a tangent line. So I would report it as a tangent line. So here it is. So points where tangent line is in the vertical, so there are no points where tangent line is vertical. And then tangent line is horizontal. And what t equals 0, which gives us the point A, would be 0 and 0. Because 1 minus cosine 0. And then at t equals pi, we get point B, which is 2 pi and 4. Because 1 minus cosine pi is -1, so it's 1 minus -1 is 2 times 2 is 4. And finally, at t equals 2 pi, what will happen? We'll get a point C, which would be what? 4 pi and 0. Did I report that? I did report it in my solution. All right, and then another exercise. So as I said, we are just doing standard calculus problems using this new technology, so not this dramatically different. Actually, it's good that we pay attention to the next problem, and here is why. Because we want to see how to calculate second derivative. So here is the function. X equals 2t plus ln t, and y equals 2t minus ln t. They didn't restrict the domain, they said just determine t intervals on which the curve is concave downward, concave upward. So concavity, discuss concavity. So what do we do here? First thing, of course, we need to see what is the domain of this function. I don't think that it's necessary really for our calculation to draw this, although it's always better to draw. So pull out your calculator, draw this function parametrically to just get a feeling of what's happening. Basically, you see, these two do not differ very much. One x plus ln t, one minus ln t. So that's why when t is greater than 1, this goes below the line a little bit, but it's fairly has asymptote y plus x. But doesn't matter. We want to discuss concavity first. Of course, t must be greater than 0 because ln is domain. Always when you analyze functions in mathematics, first question to answer is domain, so that we know which t's are we dealing with. So what do we do here? So we go x prime of t is what? 2 plus 1 over t, y prime of t is 2 minus 1 over t. Everything's perfect. So, yes, t is greater than 0, so I don't run into problems of non-differentiability. But there is one problem, and that is I can say the following, the dy over dx equals 2 plus 1 over t over 2 minus 1 over t, always where t, which how can we write this, multiplied by t, 2t plus 1 over 2t minus 1, did I flip it? The other way around, sorry, minus the top plus the bottom. Oh, and that's what it was actually. So 2t plus 1. So this derivative always exists because 2t plus 1 is always positive. So this is always differential. Exists. All right. Now we want the second derivative. So what are we doing? So we want d over dx of what we just have. But what? This is like a new function, the same way as we had f of t and g of t. I can call this to be h of t. And then g of t is the same one. So what would that be? I'll take derivative of what I had in t terms. So 2t minus 1 over 2t plus 1 over dx over dt. What would that be? Dx over dt, we already know what that is. That's 2 plus 1 over t. And here we just differentiate the quotient and we are done. So what would that be? On that quotient we get 2t plus 1 squared. Derivative here is 1, so we get 4t plus 2 minus 2 times 2t minus 1. So what would that give us? And when we distribute here, 4t and 4t cancel each other out. So we get 4 over 2t plus 1 squared. Here, if I just make common denominator, I get 2t plus 1 over t. So altogether, if I multiply by a reciprocal, I get 4t over 2t plus 1t. Here it is. I hope I got it right. Yes, I did. And then if I discuss concavity, then it's trivial. So what? I want to discuss points. So here's my t. T is greater than 0. And then I want to discuss this expression. So how do we discuss the sign of this second derivative? So here is my d2y over dx squared. So t is always positive, so I have nothing to worry about it. So the question is, what happens with 2t plus 1? It's that 2t plus 1 is also positive. Why? Because t is positive, so when you multiply positive and add 1, you get positive, but you positive, so it's actually positive all the time. So on the conclusion, we'll say the following: the curve is concave up on the entire domain. Here it is. It was fairly simple. Basically, the main thing was here, not to get confused here. So how do I get second derivative? So generally, you got your first derivative as a function of t. So then that's like a new function that you want differential with respect to x. That means another call of this formula differential with respect to t, divide, and be done. And finally, one more problem just to illustrate how do we calculate the arc length. Here is the famous for history of mathematics calculation of the length of cardioid, of cycloid. So it's problem number 55. This invention was attributed to Italian mathematician and physicist Torricelli, Evangelista Torricelli. And it was a big thing when they calculated this because full calculus was still not developed within the Hamilton and Leibniz at that time, developed their machinery. So these problems had to be analyzed through individual tricks and not with the machinery like we'll do it now with no big troubles. So x is a times t minus sine t, y equals a times 1 minus cosine t. We want t to go between 0 and 2 pi. If you remember from our previous lecture, that's what's on the top of the wheel. It goes like this. So here is the moment to a pi when you just run, actually, when your car runs the whole rotation of the wheel. And what would that be? And that happens when t is 2 pi. So what do we do here? Just call formula. So nothing here, just calculation only problem. We are square rooting, so problems are only algebraic. Everything else is trivial, so I don't even need to draw anything like that. Let me calculate x prime of t. A is here, so it's 1 minus cosine t. So I'm not writing the formula because I prefer to just prepare things, because I prepare both squares or both horizontal and vertical component of velocity. Then I'll do Pythagorean, and then I'll call formula. So I'll let this square then. So x prime t squared plus y prime t squared is to what? In the square at least you get a squared. Then here square of binomial 1 minus 2 cosine t plus cosine squared plus what is a squared sine squared t. So what do we do here? I can factor out a squared. Here what I get 1 minus 2 cosine t plus cosine squared t plus sine squared t. And then cosine squared plus sine squared is 1, and this one is 2. So I get a squared 2 minus 2 cosine t. Now comes a beautiful trick. And what is that trick? I don't like this to look like a binomial because I need to square root it, and that's not easy. But luckily, there's a formula that represents, it's like double angle formula or half angle formula. Generally tells us the following. Which way do I explain it? For example, there is a formula that you still learn in trigonometry that says sine t half is plus or minus square root of 1 minus cosine t over 2. Well, half angle formula, or you can use double angle formula, whichever way you learn it, doesn't matter. So if I square that formula, I get 2 sine squared t half equals 1 minus cosine t. So that's where I get, because if I pull out 2, of course, I get 2a squared times that 1 minus cosine t left is 2 sine squared t half. And I know sometimes mathematics looks frustrating because we always pull out a new trick from somewhere. So we just learn those tricks. We all learned it, so we didn't invent it, someone showed us, we memorize it, and that's how it works. And what would that be? So this is 4a squared sine squared theta. This is absolutely prepared to square root it, and then we will finish integration in no time. So this L equals integral between 0 and 2 pi. We square root this nicely prepared expression. So what would that be? That's integral between 0 and 2 pi. This is 2a. It should be absolute value of sine t. Let me write it like that, then I re-erase it. Why? Because if t is between 0 and 2 pi, then t halves is between 0 and pi. And sine is non-negative, greater than or equal to 0, so absolute value is unnecessary because it's always positive. And that's it, R2, R2a. Integral of sine is negative cosine, but with the linear correction, it would be, because a is 1/2, so it's 1 over a is 2, so 2a times 2 times negative cosine t between 0 and 2 pi. I didn't change the limits because I didn't do the change of variables. I just calculated it with the same variable, and that's it. So what would that give me? So what do we do? As normally, we do for a times cosine t halves between 0 on top and 2 pi on the bottom. So what would that give us? 4a times, this is 1, minus -1, which is 2, so we got 8a. And that's the famous formula for the length of the cycloid. The result makes sense. Why? Because look, this is 2a pi, so this is like 628a's, and this one is 8a, so it's longer than the straight line. So result kind of makes sense. There is an anecdote about this formula that I think it was 16th century. Professor Robert Val, he was professor of Collège de France. He actually had this result, but he didn't want to tell anyone about it. Why? At that time it was a habit. If someone comes to a college and challenges professor, and the challenger poses to professor a problem that he cannot answer, and professor then poses a problem to the challenger where challenger could answer the problem. If that happens, the challenger wins this knowledge contest, then challenger gets professor's position at the college. So legend says that Robert Val actually kept this trick as a secret if someone challenges his position. In the meanwhile, Torricelli got the result, and now the result in the history of mathematics is attributed to him. Whether legend is true or not, but we sometimes tell it like an interesting anecdote connected with this very interesting curve, cycloid.